Okay. Lecture 15, we start a new topic on list decoding. So to motivate list decoding, let's see where we are currently with respect to rate versus errors that can be handled. So we've seen two models so far. One is the Shannon model, random errors. The other is the Hamming model. The worst case errors. And that's sort of like extra pictorially we've been drawing these plots. We haven't been doing it recently, but in the early part of the course we were doing this. So let's draw the plots we have for both of these. So let's restrict our attention to the binary channels, and the only errors are flips. So in particular, on the Shannon model, that will be the BSC channel. In the Hamming model, it will be corruptions with an upper bound on the number of corruptions we can handle. So we had this sort of in both cases. I want to draw this rate versus delta curve. We want to plot these two curves. So let's see what do we. So let's delta. So let's see what we know in the Shannon case. In the Shannon case, Shannon showed that if the rate is, so it showed this first impossibility curve that this line, which corresponds to y equal 1 minus h of x. And you cannot do better than this curve, because that's the curve this curve we do. But we also at the same time went about and showed that you can existentially the exist codes just epsilon below. Basically, these two lines are the same. Just above the curve you can't achieve, just below the curve. So one is the red line is the impossibility curve, the violet line is the achievability curve. But the point is, we don't want to stop of achievability, we want actually efficient implementation of the code, for which we can also decode and stuff. And then we saw this result due to Forney's concatenation gave you code which came arbitrarily close to the binary BSC channel. So using concatenation, we were able to come. So Forney actually gave so I would say the red and the purple are due to Shannon. Green is Forney. And yeah, so we saw this. So in the random case, ignore all this. So in the random case, more or less you understand it. We know exactly the impossibility. We know these can be achieved. Shannon himself showed to come all the way up to the impossibility. And then what for the using concatenation, what you can actually come explicit codes all the and algorithmically you can go all the way up to this point. This is actually we will revisit this question later on in the course when we talk about polar codes. The question is how good is this algorithmically with respect to this? So each of them is off by an epsilon from this fraction event. So what's the dependence of epsilon with us? How is the algorithmic running time function of epsilon? Only string will be exponential in 1 over epsilon, And we will later on see polar code, which actually get you poly in 1 hour. We'll see this later on, of course. But anyway, we ignore that. Basically, in the random error model, we have completely understood it, even from an algorithmic point of view. But let's go to Hamming. The picture is not so satisfactory in respect to Hamming. Hamming, what do we have? We had several upper bounds. By the way, so this is more or less this is the point half. We had several bounds. We came up with the singleton bound, we then came up with the Plotkin bound, we came up with the Elias-Basiligo bound. Then I just claimed that there is one bound called the MRRW bound, which gets, we didn't prove this, but which gets the best of all of these things. Right now, and that's, so there is such a bound. More or less, and this is the MR, the red is the MRRW bound. It goes up to half. It's not a straight line, it's also a curve. That's the MRRW bound. Then we had among the achievability, what we had was the Gilbert-Wasserman curve over here. That's Gilbert-Wasserman, the GB bound. But then we had Ziablov and other Jefferson's things which gave you, in which you could do efficiently. So then you had actually this split into further. One was Ziablov was explicit version like below here with an explicit code. In the case of this one, there was the algorithmic and this one more or less of achievability. And then we had, could you recover from errors? The whole point is, can you recover from errors? Here, notice recovery from errors will never cross 1/4. You could never recover from more than 1/4 errors. Because if you recover from more than, you don't expect to recover more than the minimum, half the minimum distance. No? Therefore, these curves over here are very unlike over there. So here, this will be Diablo. And this is just the unique equations. So things are wide open as far as respect to salt and so things are wide open in the Hamming model. We still don't have a full understanding. The difference between these three, I would state that the red, the violet, and the yellow curve, I think is more just the fact that we have not yet been able to go. Eventually, there should be one line, and that should be the correct line. It will all merge. But notice the green line is never going to move here. It's the way we had defined it. Green line is going to stop at 1/4. The algorithmically you will never. This one is it? So, question is, have we made the algorithmic question so hard in this setting that it can never achieve what the code? So basically, Hamming's what Monsoon calls Hamming's bane. Is going to recover only if the number of errors is less than twice the number of errors is less than b, and therefore you're stuck with 1/4. That's what you call recovery, algorithmic recovery, and so you can't do better than this. Now, and that basically says the green line can never be formed. So what we want to ask is, can you change the algorithmic question so that you can still get efficiently recoverable code, but are not stuck with this to be less than b? And are these algorithmic questions still meaningful? Can we modify the question? And this is where list decoding is going to come into picture. We'll say the algorithm not only just so far the algorithm has to recover only if when the promise is that at most one code word. And there the promise has to be e less than d by 2, because if e is greater than d by 2, I can always give a setting in which there are 2 code words close to you. Now I'm going to ask, let's change the algorithmic question slightly. Let's ask this question about whether you can recover a small set of code. So even in this case, when e is exactly d by 2, notice that the extreme example has only 2 code words. I can't think of a situation that there are more than 2 code words. One. So we'll change the question. So sort of relax the algorithmic challenge. To return a list of at most L code words instead of just one. Of course, we have to ask if this is a meaningful way of addressing this question. So, but let's first define what this is. So I'm going to call, we define the notion of row L list decodable. Your row is some number between 0 and 1, and L is a positive integer. A code C. Sigma to the n. And you can think of C as given by the encoding property, given by just C. C with of dimension. That also is said to be is row L list decodable. If there exists a decoding algorithm, I'm not going to put in any computational restrictions to the algorithm. Just want right now a function. And what is the function? If there exists a decoder, it's going to take an arbitrary purported code word, and it's going to return a list of L code words. So it's going to return C less than or equal to that. It's going to return some list of L code words, at most L code words, such that the following condition is satisfied. For all C in the code word, if this purported code word that the decoder got was actually obtained by making row errors, this list should contain, in other words, one, and if the errors are
well, there's a problem because that room, Umang had booked that room for his exam.
So he booked it for the okay.
Yeah, when I told you it's okay, I had completely forgotten that he had booked it.
Okay. Can I?
No, it must be.
You have you started your class?
I was also
You got a good part of your class.
no.
How many students are there in Umang's lecture?
No, Umang doesn't. He has to put an exam.
How many students are there in the exam?
Yes.
So can he distribute them among?
I will try to ask him.
Yeah, check this. Now, if not, I can stop now and take it in Hari's lecture. Yeah. We'll have to smite this off this one. Anyway, so if you have a code word and you add this noise to it, and you give the decoding algorithm this as your code input. What I want, the promise is that the decoding algorithm should in fact output this original code word as one of the elements. It outputs a list, and the list is guaranteed that if this code word was obtained from the fact from by not making more than row in errors to making row and errors to the code word, then that list should actually, the list that the decoder output should contain this is what we would want from a list decoding procedure. By the way, we have already seen something like this when we did the proof of alias plus before. Equivalently, this can be said in the following fashion, which is without talking of any decoder or something. Equivalently, this is the same thing as getting point C is row n list decodable. If for all y in sigma to the n, if you look at the ball of radius rho n around this one intersection the four, this should contain at most. You can convince yourself these both are the same. The first one I have written it as an algorithmic statement. The second one is a purely combinatorial statement. And you can check that the first one is also just an algorithm. There's no algorithm. However, later on we'll ask the algorithmic complexity of the decoding. This is a question we'll come to, possibly not in this lecture. In next lecture, we'll ask this question. Okay. So you're given a code, we're going to ask what are the row L parameters for which it is decodable. So certainly we know every code is list decodable is delta by 2, 1 list decodable. That's what the unique decoding radius is. And the whole point of the definition of list decoding is to allow to move this curve from more 1/4, possibly go all the way to the distance. A couple of remarks are in order. One, and this is not a computational definition, it's a combinatorial. But combinatorial. Even more, is it a reasonable definition? And there are several answers to it. Most times we show that this list size for a random, if they error, what happens in observed practice is the row and error happen randomly, not worst case. And we then check the new y, the y that was obtained by taking a code word, adding row and random flips and looking at the new y and decoding it. Most such cases, actually the list size was only of size 1. So this definition allows you to recover from those things which previously we said we will not even recover. So the random error, this is something I'm stating out of the box, but this happens with me. In random errors, the list sizes is typically 1. Even for row being much larger than delta by 2. That's one thing. The other thing is, you might say that having list of size greater than 1 is useless because how do I tell you? I can recover and I get 2 code words. How do I know? You might have some other side information about the code word. Or you could possibly run 2 recovery processes or something which will help you disambiguate. That is, you possibly have side information to disambiguate. From the list. So it might suffice that even if so you have narrowed down your potential choices from exponential and you say one of these L choices. Now use some other whatever piece of information you have to pick to decide which is the one. In some other cases, you might also see that actually you can use side information. This might be possible in cryptographically bounded channels. The list size will even, that is, if you say that so far we have been talking of random channels or worst case error channels. Sometimes you can assume that the channel is also its worst case, but it also has computational bounds on it. The channel is also an entity, a computational entity, and there are bounds on it. So if you're trying to work with them, whether the channel can produce, and there are cases in which you can show in those cases also, actually this list decoding will work. I don't know if Akshay covers any of such things in this course. We will see if we can have time, we'll go to such application. I'm not sure whether we'll have time. There are a lot of additional topics I have on the potential topics to the end of the course. So these are some ways in which we can address this question. But right now it's a meaningful question. We'll ask, are there codes that satisfy this problem? Notice that we already did see this, where there is in the proof of Elias Basilico bound, we did use such a definition. So in the coding theory community, there was this decoding present. It was used more for proving bounds and all. It was never used as an algorithmic tool till the early 90s. Till the early 90s, or rather the mid 90s, when we discovered that certain codes are actually efficiently list decodable. Till then, we knew about list decoding as a concept, but we never actually worked with it as one because we didn't have explicit codes which were efficiently list decodable. And in the mid 90s, it was sort of discovered that the Reed's, one of our favorite codes, the Reed-Solomon code, was efficiently list decodable to something well above the unique decoding radius. And this was actually one of Monsoon's fundamental contributions. He showed that the Reed-Solomon code is list decodable above the Johnson, above the unique decoding radius. And since then, list decoding has become a big sort of, we try to understand the list decodability of various codes, and so in the last 25 years. Okay. So there's a definition here and this one for list decoding. So our goal for the next half an hour or so and for the next lecture is going to be this. Okay, we are now given a definition for list decoding. Fair and nice, but what are the limits of this definition? Does this put an upper bound on the rate? If I say a code is row L list decodable, does it say the rate can't be beyond this? So that's sort of like the impossibility result. And does it also tell you, can you show code which achieve this, possibly probabilistically or some construction? That's sort of the achievability curve. So we'll try to understand these two questions. The same sort of questions which we looked at in the Hamming case and in the Shannon case. We'll ask, is there an upper bound you can put on the rate of the code? Is there a lower, is there an achievability code? Then we'll ask, can we get codes which are achievable all the way up to this point? And furthermore, then we'll ask, are there explicit such codes? And furthermore, can these explicit codes be accompanied by efficient decoding, list decoding algorithms? This will be the topic for the next few lectures. We'll start off with the limits on rate. Limits on rates of row L list decoding. So let's do this first. Suppose C subset of sigma n is, let's take this, the factor sigma n, sigma n is row L list decodable. And the rate of the code is quite large. The rate of the code is more than 1 minus the query entropy. It's an epsilon more than this. Then I want to say that actually this case list decodable is not a meaningful concept. there will exist words. If the rate is so large, there will exist words for which the list size has to be exponentially large. Then n will be greater than 2 power. Okay. Statement here. This shows puts an upper bound. It says, since it says that the rate can never be larger than 1 minus h cube. If you're talking about list decodability of codes in which the list sizes are sub-exponential, for it to be meaningful, we want sub-exponential size lists. Actually, we want constant size or even poly-size list sizes. But even if you want it to be sub-exponential, you cannot be talking about rates which are larger than 1 minus h cube. The moment you go above that, there will be words for which around them there will be exponentially many codes. And let's see a quick proof of this. The proof of this will be similar to Shannon. How would one expect to prove this? So we need to show that there exists a purported word. So I'm giving you a course. So basically, what have I said? I'm giving you a. This is the space. Sigma n, and these are the code words. What I want to say to you is there exists a word y such that around it, in a row and ball around it, there are way too many code words. So we have to lay our hands on such a y. You pick the y randomly and show that a random y has this code. I know nothing else about the code except the rate of the code. So let's choose y. Choose y at random from sigma. And what do we want? We want, let's ask this. Pick a particular code in the code word. Let's ask the probability over y. What's the probability that y is in the code word is within a ball of let's ask this. What will this be? Yeah, it's one of the balls with the first thing of that is the other way around. It's the same as probability of y in the ball C over n. So this is exactly the volume of the row n ball by q power n. This we know is on greater than equal to q power minus n. So 1 is from the denominator, then you have 1 minus HQ rho minus a little. This is by our bounds on but this result is true only if rho is less than or equal to 1 minus 1. But we needed this bounds. So now let's look at the expected size of C intersection ball y rho. This is a random variable. Let's see. What is this? I can just go over expected over all C equal by linearity of expectation. This is the same as probability that C is in ball y rho n. I'm counting a particular number. This is basically for every code word I write this. No, it's this. So what is this? This is exactly the previous q power Rn times stuff. Let's just write that down. That is greater than or equal to q power, let's write it, minus n, 1 minus h rho q minus r minus the rho. Yeah, but now if R is a little more than this numerator will be a positive quantity. The positive quantity modulo this negative sign, therefore it will be q per something, so this will be a number. It will be a number. Quickly, you can show that this is greater than or equal to q power minus epsilon m if R is greater than 1 minus h q rho plus. And so on an average, a ball has this, an average y has it. So certainly there exists one y for which this ball is. Huh? Yeah. So they exist, so the hence y, hence there exists a y, in fact a random y. Exponentially moving forward. Row and ball. So this tells you cannot expect row. If you are talking about row L list-decodable code, you cannot expect the rate of the code to be better than 1 minus the query entropy of it. That's the best you can achieve. Now you can ask the other question that Shankar asked: do there exist code which go all the way up to this? So that's going to be our next. It basically says yes, we can go all the way. With anything slightly below this, you can go all the way. So let L be any positive integer. Then there exists row N list-decodable code with rate greater than or equal to 1 minus h q rho minus. You can go very close to 1 minus h q rho. The only thing you'll be below it is by a factor 1 over L. That said, you cannot go above it by a factor, any epsilon factor. This says you can make L to be as large a constant as you want. Therefore, you can come closer and closer. You allow larger and larger L, you can come closer and closer to this curve 1 minus h cube. Somehow it's assumed that L is sufficient large. Yeah, all of these statements, when I mean them, they will be that it states that give me such a code, there will exist I'll give you a family of codes such that from a particular n onward you have this. Yeah, I'm not. That's what the actual, if I write it formally, that should be received. Because there will be a Chernow bound or something that will happen in the group and will be. Okay. And how do we go about doing this? This will also be simulation. What's the best way? I want to just show that an existing code. Pick the code at random. So pick. Let's work with that rate. So just basically pick P at random. Huh? No, with rate at least so much. So we'll show rate exactly from here. That's the achievability. Yeah. So when I say achievability, if I say rate less than equal to, certainly I can give a rate which is much smaller and the theorem will be true. Yeah, that depends on how you word the. What do I say pick C at random? That is for each I going from 1, 2 all the way up to 2 to the power Rn. Pick Ci just at random from sigma. For each of these, just pick a completely random. Any complete random and independent. And what is the bad event that we have to be fighting against? The bad event we have to be fighting against is the fact that there exists some y and L plus 1 code words C0, C1, all the way up to Cn, such that Ci, Pj is in the ball, is in the row and ball around y for all 0 less than j less than 2. That's the bad. And if we can show that if we can show the probability of the bad event is less than 1, then there is a code for which this bad event does not happen. So that's basically it. So for now, let's fix a y, and let's ask for a particular Cj, what's the probability that Cj is in the ball y row. This is exactly the same calculation which we did before. This is the volume Q n row n Q n 4, and this we know is less than or equal to Q power n minus 1. Now this. Now we not only need this condition for one, we want this for all the L. This one. So basically we are asking now the probability of C0 all the way up to Cl for all j going from 0 to L. Cj is in the ball y row. Yeah, this. And because of the way we are taking it, these are all independent. Well, so it's just that to the. So this is less than or equal to. So this is less than or equal to Q power minus n L plus 1 times 1 minus h. Okay. Now what are we asking now? Asking the probability of the bad event. What is that probability that there exists a y and that there exists T0 to Cn such that okay. Let's do one gigantic union bond. So there exists a y, that's at most there are q power n of them. And if I have to pick C0 to Cl, this could be any of L plus 1 code words. How many code words are there? There are totally q power Rn code words, and I'm picking L plus 1. So let's picking some set of L plus 1, and then it's that. that okay? So let's now just simplify this. This is q power n. So I'm going to write everything in the exponent q power n. This I'm just going to approximate it by q power. I'm going to upper bound it by q power rn to the power n plus. So this is, let's take out n completely. So it's a 1 plus r times n plus 1 minus n plus 1 plus minus n plus 1 into 1 minus now if we had setting r equals 1 minus HQ rho minus 1 by L, what will it turn out to be? So these two terms will nicely cancel out. The only thing will be left with will be a just be equal to q power n 1 minus n plus 1 by L. That's what I got. I'm wrong with that together. So actually, let's set this to be minus n by L plus 1. Okay. Then what do I have here? 1 minus 1, everything gets cancelled out. Somewhere I need a strict inequality. So let's choose R to be
One line will work.
one by L works.
Yeah, because L plus 1 by L is 1 plus 1 by L.
I think anything small, if R was anything smaller than this, that should have worked, no? But yeah, that would make this a strict inequality, and we have some so this is equal to 1. And we have yeah. Okay. So in other words, so list decoding is a thing in which at least now we change the definition sufficiently so that the achievability and the impossibility curves are exactly matched. So now the question comes is, this is not satisfactory. We want actually nice codes that are okay. So the rest of the list decoding discussion is all going to be coming up with nice codes which have these properties. Okay. So hence the impossibility and achievability curves the next question is first questions are there explicit codes which achieve which are less equal to and then less decoders be made efficient. Okay, so that's going to be the next question. We're now going to we'll go back to our existing code we have studied and ask up to what point are they less decodable? Does that and do they achieve the this kind of 1 minus h2 row which what? Furthermore, if they're less decodable, can I accompany those less decoding things with actually efficient less decoders? And we already saw a statement of this nature. We saw that for every code, if you give me the distance of the code, there is a particular point called the Johnson radius up to which the list sizes are formed. If you recall, we had done this. Okay, so binary code, we had done this. We had defined something called the Johnson radius. The J2 delta, we had shown and basically we had showed the following nice lemma. So given any delta in 0.5 and C is the n or n delta n 2 4. Basically a code with some distance delta. Then for tau being equals J2 delta defined above, for all y in 0, 1 to n, we have shown that the ball radius tau n intersection around y has at most n plus 1 coordinates. This basically says that every code word, if you know the code word has distance delta, then you can go all the way up to the Johnson radius and still guarantee less decodability, but the less decoding radius L is now n plus 1. We have given a full proof of this, and this is a sort of extending Plotkin's proof, and that was done for the binary code. There is also a query version of this. Query version, which is JQ delta, and it's the natural that half will get replaced by 1 minus 1 over q, and 1 minus square root 1 minus q delta by q minus. That's the query analog of the Johnson radius. There's also an alphabet independent version. This is, and that basically goes by observing that JQ delta, which is this quantity, which is a definition 1 minus 1 over q, 1 minus square root 1 minus q delta by q minus 1 is always greater than 1 minus square root 1 minus q. For any value of q, it's always larger than this. Therefore, we will restate the Johnson. The Johnson bond sometimes is just stated. If you don't know the alphabet, it's just stated as this is the Johnson radius. Up to this point, which is a smaller number than if you know the alphabet Q, you can get a more refined transfer radius. Otherwise, it is smaller than. Up to this point, the list size is always bounded. Okay. So given the fact that this decoding is such an important thing, we will give an alternate direct proof of just this statement. And actually, the proof will be strong enough that if you tailor it, if you look carefully at the alphabet size, we'll be able to get these more. But I just want to give the proof of this. So now give an alternate and this, if you recall the original proof of the Johnson radius, use this geometric lemma, sort of use the plotkin, use the going from the Hamming metric to the Euclidean metric, and then we did it. We will not do that. We will give a combinatorial proof. Also called the Johnson bond. Formally, we do the following statement. C. Okay. And more than delta and shift 4. So we put 1 minus 2 1 minus delta or y. The ball y of n intersection 4 is the lowest of order.
Yeah, already significant. Already.
In fact, I think we get n by 4. I think we get n by 4. I can come and change that. Let me. Let's leave this blank for now and I'm going to fix this. And we finish the proof. So keep it 3 now for now. And this proof. This is really right. Basically, what we're going to do, we're going to sort of do a sort of counting argument. So suppose I give you a Y and L code words. I give you, so suppose there exists a Y in Q to the N and C1, C2, Cl over to C, such that Y belongs to ball Ci tau n for all 1 less than equal to I less than equal to L. We want to show certain things happen. One, what is happening? So there are 2 things happening. That is because the ball Y is in Ci. Ci and Y share a lot of agreements, but the CIs among themselves are fairly distinct because they are forward, they are at least delta apart from each other. So there's sort of a tension between them. On one hand, the CIs share a lot of coordinates with Y. But on the other hand, the CIs amongst themselves pairwise are very different. So this we'll put both of these together to show that there cannot be too many such CIs. So let's consider the following bipart. Let's make, I'm just going to make more. Consider the following bipartite graph. So the left hand side is basically 1 to n. I'm going to put, what I'm going to put is a coordinate. I'm going to label it with y1, y2, yn. The right hand side is going to be L. And basically I'm going to label these with C1, C2, all the way up to C10. I'm going to do the most natural thing. What should I do? When will I put an edge? When will I put the edge between, let's take an arbitrary Cj and the yi. So when will this edge here? So edge ij exists if and only if so the Cj's height coordinate is actually equal to y. So let's put edges. So that's the graph. Is the graph clear? So whenever Cj agrees with y, so basically notice that for every vertex here, you have what is that degree? That's n minus tau. Yeah. Okay. And so that's the one. So okay. So I want to say it's a lower bound, right? Yeah, it's a lower bound. It's a lower bound. Every vertex, every right vertex has degree at least n minus n into 1 minus tau plus 1. Yeah, and every that's the thing. But we know that if you let's drop the plus 1 for now. It's not going to affect my calculation much. Let's put over 1. So let's also look at from this side. Let's look at the degree from this side. So let this be the degree, say d2, dn. Basically, this is the number of coordinates on which the di is the number of code words in this list of L which agree with y at the ith coordinate. Huh? So di is number of j in L such that dji equals y. Huh? Oh. Yeah. Is that right? And let d bar just be summation di by n. It's the average degree on it. Should
With L for this.
yeah. Now I understand why Madhu put the bipartite graph and Madhu did the notes is the other way around. So what do we know about this? The number of edges will be found on both sides. We do know that b bar times n is the number of edges when you count from this side. This is at least n times 1 minus tau times n. So because of this, number of edges from both sides. We have d bar times n is greater than or equal to n times 1 minus tau times L. That implies d bar is greater than 1 minus tau times L. Okay. Now, what I want to do, we want to understand the condition that two code words, two CIs are not going to have too much agreement among themselves. So let's pick I1 and I2 at random. For the and let's ask J1 and J2. Let's ask what is the probability that I is adjacent to both J1 and J2. So here I is a fixed coordinate in one. So I picked two guys, two separate guys, J1 not equal to J2. Two separate guys, and I ask, and I have a fixed I ask what's the one. So if you look at this graph, what will this be? Yes, this is exactly going to be, this is exactly di choose 2 by L choose. Okay. So, in other words, the expected number when I pick a J1 not equal to J2, the number of common neighbors of J1 and J2 is just going to be summation di by 2 by L choose 2, I going from 1 to 2. Right? But we know the number of common neighbors can't be too large. This is because the Ci and Cj are two different. Cj and Cj prime are Cj1 and Cj2 are distinct code words. So this I want to actually, I don't want to work with summation bi, I want to use one. So I want to say this is, I want to bound this from, I want to just, I will just use the following, but I want to say this is n times d bar by 2 L choose 2. Why is that? Yes. General thing for it. So x into x minus 1 by 2 is a convex function, therefore that the average of those is at most this average, therefore because it's the average, there's an n that will come out. I just don't want to carry dx, so I have this. So what do we have at the end of this? We have this statement. We have n times d bar by 2 is less than or equal to L choose 2. But here I do know I have an upper bound on it. This cannot be more than n into 1 minus delta plus 1 minus 1. Let me write this a little more. Therefore, I want to say, on the other hand, for every J1 not equal to J2, the number of common neighbors is common. It's always less than or equal to n into 1 minus delta minus 1. Because that's the distance of the pole. Therefore, the agreement has to be strictly smaller than this. We just put all of this together, we are going to get that. Putting these two together. We're going to get that n times d bar 15 is less than or equal to L choose 2 times n into 1 minus delta means. Let's open this up. We're going to use one factor, we're going to use this. So let's go ahead on to the right first, then on to put that. Right. N into L minus 1 by 2. N 1 minus delta minus 1. That's the right hand side. The left hand side is an n over here, floating n. And I think I can replace this with 1 minus tau L. Because I'm just using d bar is greater than or equal to 1 minus tau times. So 1 L will disappear off the picture. When we mess up the calculation, the actually comes up very nicely. So I'm going to knock off that L. The L can be knocked off. The 2 can be knocked off. So what do I have on the right hand side? I have 1 minus tau square times L. Minus Ln minus 1 minus tau times n. That's what I have on the right hand side, left hand side. What do I have on the right hand side? I have L minus 1 n into 1 minus delta minus 1. Here we use the fact that tau is defined to be 1 minus square root 1 minus delta. Tau is in fact any number smaller than this. Therefore, 1 minus tau square is exactly 1 minus delta. So that's set it up so that to cancel out these two things. So this will, so I'm going to replace this will become 1 minus tau square ln minus 1 minus tau n is less than or equal to L minus 1 times n into 1 minus tau square minus 1. One more man. So the 1 minus tau square ln will just cancel out on both sides. There is a minus L. So let's bring all the L terms to this side. So this L term has gone off. This L term has gone off. The only L term that's remaining is a minus L. So that I'll bring it to that side. That is L. And what are all the other terms that are surviving? There is a 1 minus tau n that goes that side. And I think there's just a 1 minus tau square n. And then there's possibly a plus 1. Okay. This is just 1 minus tau. 1 minus tau. 1 minus 1 minus tau, that is just tau. N plus. That's the inverse to it. Therefore, that's the boundary. You get, I think this is more n by 4. For in tau less than or equal to this, we're going to get tau into tau. By the way, there's a method to this sort of counting it is called the Rankowitz method of compounds, and this is quite common to do. This is just implementing the Rankowitz method for this particular problem. And actually, you can, if you're a little more careful with the alphabet, you can recover even the alphabet dependent versions using the same proof. So the book, Guruswami Rudra Sudan, does it for the case u equals 2. You then go and insert it further, you can get it for arbitrary q also. The same proof it will do it, but for q equals 2, it will take this proof and actually get J2 delta instead of what I put J delta. So this is usually called, this quantity is usually called J delta. This is the alphabet independent.
So once you get the relation of the indices where Y and C agree, then you get the deep space size is large, but the median intersection is small.
Yes.
Then currently apply on positive on the because you know
Which inequality will be put? It might be the same proof.
the positive function is in the PL, you get only the first two terms. That is then equal to the.
But it's by that you just mean the usual. What do you call it? It's a second step of the union bonus one step, the next step. This might be exactly the same proof. All of it is within one interpretation. Might be the same proof. Yeah. Okay. Okay. So what's all of this? This is all to say that every code is actually, and 1 minus square root 1 minus delta is always a number greater than delta by 2. That's another crucial thing to note. This is a number. This quantity is always greater than delta by 2. So the 1 minus square root 1 minus delta is always a number. So it's always a point larger than the minimum number. So it's the Johnson radius, the proof which I said so far is you can always go a little up beyond delta by 2 and still guarantee that the number of code words is polynomial. In fact, if you do this proof a little more closer, so right now I have taken tau to go all the way to this point. You can ask, what if I go minus epsilon less than this point? Then actually, if you look at this proof largely, the dependence on n also drops off. This will be only a function of epsilon. So if you're at the Johnson radius, you get a list size which is linear in n. Even if you're epsilon away from the Johnson radius, you get a list size which is independent of n, which is just a constant. It's something like 1 over epsilon squared. The same proof, if you do it, either you do this proof or the geometric lemma proof, you will get that when you're a little away, you actually get the list size to be constant. It won't even be a function of n. So now we can ask the question, go back and look at all the code that we have seen so far. We've proven distance for them. So they are all list decodable up to the Johnson radius. This one statement already proves that they are all list decodable up to the Johnson radius. So each of them. But then we could ask the next question, okay, they're decodable up to the Johnson radius. are they actually efficiently list decodable up to the Johnson? This only shows that the combinatorial list decodable. Can I come up with algorithms for list decoding these codes up to the Johnson radius? In particular, we'll start off with the nicest code that we know of, Reed-Solomon code. We'll ask if this code is list decodable up to the Johnson. And we will show this was proved in two sequences of work, one by Monsoon in the mid-90s, and then followed by work with Madhu and Shankar in 98. They together show both these work together show that the Reed-Solomon code is efficiently list decodable all the way up to the Johnson radius. So this will be the focus for, I think I will stop this already 11. This will be the focus, this will be the topic for our next lecture. And the way we will show that is that I actually will go look into the Burley-Camp-Welch decoder for Reed-Solomon code. If you want to extend this to allow for output list, what are the modifications we have to do? Go ahead, do those modifications, and miraculously that will suffice to push it all the way to list decodability. So this will show that the Reed-Solomon code is list decodable all the way up to the Johnson radius. Note, but the Johnson radius is not the list decoding capacity. The list decoding capacity is 1 minus HQ delta, and the alphabet is this one, that's 1 minus that's delta. So you must be able to, even if you make delta fraction of errors, you must be able to recover from. The question is, Johnson radius is one bound up to which you can list decode. It says every code with distance delta, but there might be code which can list decode even possibly beyond the Johnson radius all the way up to what were guaranteed by the achievability and the curve which we showed before. A random code which we showed just now goes all the way up to that. Forget about Johnson radius. Goes all the way to 1 minus HQ delta. We can then ask, can we come up with explicit codes that achieve this? It's an open question if the Reed-Solomon code is actually has this property. In fact, is the Reed-Solomon code list decodable beyond the Johnson radius? This is an open question. We do know now some in the last couple of years, there have been some partial results which show that Reed-Solomon codes do achieve some sort of, depending on the choice of evaluation points, they can go beyond the Johnson radius. How much beyond, we do not know. What we'll instead show is we'll take another code very closely related to the Reed-Solomon code called the multiplicity code. So if you have done the second problem set, you would have seen this, in which we not only give the evaluation of the point, we also give the evaluation of the derivatives at that point. This is called the multiplicity code. And we'll show that this code actually goes all the way up the capacity. Depending on how close you want to go to capacity, you have to give so many derivatives. And then you can go all the way up to this. Both this code and there's another. You would have seen two codes in the second problem set, folded Reed-Solomon. Both of them go and achieve capacity, list decoding capacity. In lecture, we will do multiplicity codes. Most of the other lecture notes available online and in the GRS textbook, they will prove folded Reed-Solomon code which achieves capacity. And not a subset of multiplicity. I defined in the problem set, we defined something called these polynomial ideal codes and two special cases where folded Reed-Solomon case and the multiplicity. Yeah. No. Multiplicity code is multiplicity. So Reed-Solomon code is in which, so you have E1x, so let's go back to the problem set. N polynomials like this. In the degree of each EI, it's in fact exactly equal to S. Exactly yes. And the encoding of a polynomial, and let's also say the EIs are pairwise co-prime, that is, they don't share any factors. And furthermore, let's look at the product of the EIs. The degree of this is the degree of this guy because of this is equal, exactly equal to Sm. And let P be some polynomial of degree less than or equal to k, which is significantly smaller than S. So the encoding of P will be. Can you turn the camera? The encoding of P is going to be P mod EF. I going from 1 to 2.
And we have to.
Yeah, so 1 second. So let's look at various special cases of this. Special cases of this is when EIX is just x minus alpha I. This is the read problem. Because then P mod x minus alpha I is just P of alpha I, so this is the read problem code. Another special case is when EI of x is x minus, so this is the case when f is equal to 1, x minus alpha I to the power s. Here, what are you giving? You are giving its mod this one, but that's equivalent to sort of giving the first s derivatives. So this is what's called the multiplicity. So I want to say P mod EI in this case is equivalent to giving derivatives of P up to order less than order s. This is what's called the multiplicity code of order. Order S. In particular, multiplicity code of order 1 is exactly the Solomon code. The third example was when EIX was x minus alpha I, x minus gamma alpha I, x minus gamma square alpha I, all the way up to x minus gamma to the power s minus 1 alpha I, and gamma is some generator or something, and then notice that P mod EI in this case by Chinese remainder theorem is equal, sort of, it's the same thing as giving P at alpha I, P at gamma alpha I, P at gamma s minus 1 alpha I. This information and this information are the same. This is what is called the folder transform. So they are all sort of special cases of this polynomial idea.
Gamma equals to 1, then.
Yeah, but gamma has to be a generator for this proof.
Yeah.
So, yeah. So question is, can we put them all in one single thing? I don't know how to do it with that. So the proof folder become good. It is true if I put gamma to be equal to 1, I get the multiplicity code, but I don't know how to. The proof for folder transformation uses the fact that gamma is a generator. Certainly 1 will not work. Yeah. And what we show is both these codes achieve capacity. Standard books will give you this. In our lecture notes, what we will show is we will work more with multiplicity codes. That will be the sort of sketch for the next few lectures. We will first show the column code, will give the efficient decoding after the Johnson radius. We'll then modify, then take the multiplicity code and show that not just Johnson radius, it goes all the way to the decoding capacity. And that will be for the next couple of lectures that will be about. And all these tools will have the same template. We'll take the Welsh-Barley decoder and try to generalize it. And the same generalization process will be. Next class.